everyone, Paul. You're at the very first episode of Open Source System Breakdown. And just give a lot of context what we're doing here. We're basically going to go over really amazing and interesting open source projects and talk about sort of why the project got started, what is the motivation behind it. And we're going to dive into some interesting tidbits about the project itself, like what are interesting challenges you had to go through, and also a demo about what the project looks like. So, hey, welcome, Paul.
Hi, thank you. Okay,
Yeah, so
hi.
Tell me, give us a little bit of background on who you are and why do you even start this project? And yeah, some content of the project will be great to start with.
Yeah, for sure. Okay, so hi, I'm Khuong. I'm a staff engineer at OSS Labs. Started at Backtrace and then was acquired. So what Backtrace does, it's an error analysis platform. So you take your application out in prod and like consumer devices, whatever. And then every time something crashes, something goes wrong, you send the data to us. We store everything, we index interesting data about it, and then you can go into UI to try and drill down into like exactly what's going on with your application. You know, what happened this last release, is this new, like what's going on. And that, hopefully helps you triage bugs and problems with your devices, and then you release a like more polished product more quickly. And so the way we do storage is kind of interesting because there's a lot of like contractual requirements around like storing that kind of data. So a lot of the bigger businesses, they want to run everything on their own devices. Some will even say, we just want to run it on our like on-prem in our own data centers. But like we've been targeting game developers a lot in the past couple of years. I think it's a good market, and smaller game devs, they want something small that can scale down in cost. So like it's how do you have an architecture that can go up and provide like these kind of guarantees on isolation, and it can still also scale down and like do a very cost-effective multi-tenant solution. And the way we ended up doing this is, yeah, go ahead.
Yeah, I agree. So yeah, I guess we also want to touch on later on, like, yeah, using SQLite, and maybe exactly. That's the choice of using that is because you want to be very ubiquitous, have a very easy install everywhere, or.
Yeah, that's it. And that's how we got to like SQLite for all our like, so bulk storage goes in files, but otherwise everything else is in SQLite, because that's the only solution that is like kind of scaled down very easily. And then when you run on-prem, like you don't really know what's going on. So we ended up with this solution where every single like piece of interesting metadata is stored in an SQLite database. And so we have like thousands of SQLite databases just for our hosted solution, because all the data that we care about is shards very nicely on like projects. So like if you want to analyze crashes for like application A, you're not going to look at it. Hopefully you don't have to like join the data with application B, because then like becomes very interesting.
Got it. So Verneuil, right? Or Verneuil, is that how you pronounce the project?
It's a French name, so Verneuil.
Okay, so I'm probably butchering it even more, right? But this is like from reading from a GitHub repo. It's a VFS abstraction for SQLite, but also like replicate your snapshots to S3. And so this is more of a this is not a cluster, right? This is actually a single SQLite that gives you this abstraction that can easily snapshot. Why do you even build a VFS? Like, why could you just snapshot a SQLite project on its own? Like, why do you have to do like a file system thing here?
Yeah. Okay. So I mean, some people do that when they need to like distribute or take backups on an SQLite database. You just try to get like a quiescent period, like maybe to acquire a read lock in the database, and then you just upload the whole file. And that's done. Super simple, robust, easy to understand. The problem for us is that we have like a very wide range of database sizes, even though like we cut our data down in like physical shards, but like as fine as we can. Like we have a couple of databases in the like 1-2 gigabyte range. So taking a full snapshot of like 1-2 gigabytes, it's gonna take a while, like kind of pick up your application, not a great user experience.
Oh, interesting. So who will be running this in typically? This is your customers, right? Like you mentioned, that they will install this locally to store your space, right?
So this is all on the back end. Once the data has made it to the cluster that either that we run or that our customers run.
I see. Got it. Got it. And so this, okay, interesting. And so this is really just actually providing a way without having any read-write locks to your database and do single copies. Like, so you're transparently, by building a VFS, your files, I guess because you understand when you're actually syncing the files, when you're actually doing the reading and writing, you know exactly when to snapshot and when to replicate. Is that
Right.
a choice that's part of this project, or?
Yeah, so like I think a big design choice was to make it so like when you integrate Verneuil to get replication, you don't have to change anything because we have like a lot of code that already uses SQLite. And like we want to make it transparent, so like it just works the same as if you were just writing to your local disk. But because we work as an SQLite extension, we know when's a good time to take snapshots of the file. So as soon as SQLite says, okay, this is safe to read, then I can figure out what the diffs are and queue that for upload to S3.
Ah, interesting. Got it. Got it. And so how do you actually able to know that if you're just a VFS layer? Because VFS layers, you see all the file system operations, right? But
Right.
do you actually query the CLI? I guess maybe this talks about the design of the project a little bit. Yeah, I'm just curious, like how does it actually fit together?
Yeah. Okay, so like I said, like we have this code, it already works. So like there's a lot of design constraints around like how we can integrate with SQLite. And one of the key constraints was we have to keep using the rollback journal. That's a default storage mode for SQLite. And so the way rollback works is that when SQLite wants to commit a write, it acquires a write lock. It writes rollback data, so in an undo journal, it does its writes to the SQLite file, and then it releases the lock. And so there's this property that whenever SQLite releases a lock or relaxes a write lock to a read lock, unless the journal file is still around, so that means something went horribly wrong, then otherwise the database is safe to read. At that specific moment, as long as no other write comes in, the database is in a good state that's like coherent and you can take a snapshot from it.
Got it. Got it. So it's really about the time when you want to take a snapshot, right?
Yeah.
And interesting. Got it. And so when you take a snapshot, I guess, because it looks like you actually quite have a lot of choices here. When to take a snapshot, what to snapshot, right? You're doing the diffs instead of the full, and sounds like there's one part of the goal is to actually get the performance to be fairly high. I guess, what is the choice, because SQLite is already a big choice here, it's a single node, definitely much more simpler, but of course it's not the most highest performance, database, I guess is really well understood at this moment. There's no other projects out there that worked at all? And I guess that's my first question. Like, why can't probably even do this in the first place?
Right.
And if none of that works, what is what needed to change to make it work? You guys.
So we looked into a few options for like in a distributed or replicated SQLite space. A lot of options target something like HD or something like that, where you have a multi-writer, you want like to beat a reflection to figure out who has a right to update the database. And we don't want any of that, right? We already have this system where, it's only one writer, the file is on local disk. We don't need that complexity. We don't need these new failure modes. And then there was Lightstream, which works with a wall. So that's kind of the problem here, is that we have our application that works well in the rollback mode with its performance characteristics. And then if we switch to wall mode, then what's going to happen? We're not sure. So we try to be extremely conservative here.
I see. What does it mean when you switch to wall mode? You don't know sure what it means.
So the SQLite behaves differently. Like it's a completely different way to update the file. So like maybe like code that for now has worked fine, and will have just randomly just start misbehaving in wall mode. And there's also the question of like, so we don't control deployment, right? Because we also sell this on-prem. Then like if you say I have a dependency on this new daemon, that's something else for you to maintain and like to figure out what's wrong with it whenever you have to debug an installation.
Interesting. Got it. Okay. So definitely, basically, it sounds like you're really playing with the limits of SQLite.
Yeah, we're playing with the limits of SQLite, and we're playing with the limits of like this, fairly large 7+-year-old system that
yeah,
we don't want to change too much because it works.
yes. Got it. And so you're doing asynchronous replication, right? And able to like making sure you take the right snapshots. And did I hear there's also distributed mode? Or like, what does distributed means here? Like, are actually taking snapshots in multiple places, or this is...
No, I'm just saying like whenever we're looking for like replication options, like streaming replication options, it was always people trying to solve the harder problem of like distributed SQLite, which like we don't want to get into because we don't need it, and that's a lot more complexity.
You just want a single node. Got it. Yeah. And so I'm looking at your description, and there's data, like you talk about data freshness. It's not a goal for you guys, right? You're prioritizing disaster avoidance over anything else. And you have a very particular way of doing your replication buffers. So talk a little more like it sounds like you want to make sure that things are consistent, right? You're doing the right snapshot instead of having making sure you have the latest states of what's in the files, right? So you can able to read it correctly. It sounds like that's what you're doing, right? And
yeah,
and like how, yeah, I guess I'm not entirely sure what is this wait-free crash safe replication buffer is, and tell us about like what is going on here for you to make the right choices, and what are some of the problems you kind of have to solve. It sounds like that's one of the problems you have to solve, right, to make this work.
So like SQLite is special because it runs in multi-process, and it's crash safe. So if your process is writing to an SQLite database and crashes, the next time it comes up or next time another process starts reading from the database, it will just recover as if nothing had happened. And so that's very different from like what you might have like when you have a client server architecture, because then all the writes are handled by the server, which you kind of assume doesn't crash essentially. So that because we run in the same application, like our replication logic also runs in line in the same process as the writer, we have to maintain the same guarantees that if you crash, we will not start like replicating a broken snapshot.
Got it. Interesting. Wow. And so, yeah, like, so maybe in a nutshell, tell us how exactly, because we talked a little bit about the challenges sort of high level. Actually, just want to go into deeper, like, how does this work? How does when you run this, right? You install, I'm sure this is like a VFS layer. So you do a fuse mounts, I suppose, right? And get there, like what happens? Tell us, go through maybe like a quick life cycle of how this works in general. Yeah.
All right. So SQLite has a VFS layer internally.
Okay.
So that's what makes it like kind of not too like
okay. So you have to do
extreme.
Like yeah. Got it.
So you can register your code as a new VFS type, and you can say by default start using this VFS instead of the like Unix VFS layer to do all your writes. So that's what we do. You initialize the Verneuil library, and it will register its VFS in SQLite, and it says by default you now use Verneuil if it's configured that way. All right, and now what's going to happen is when you open a new database, it'll go through Verneuil to do its file operations. And so we have this base code that is completely like 100% compatible with the Unix code. So like there's no difference on the outside. It's just that we use like syscalls that were introduced in maybe the late 2000s instead of stuff that's been around since the 80s.
I see. Okay.
And that's how we can then track writes. So whenever you do a write, we can take a note, okay, well, that range has been dirtied. If we need to take a snapshot, we're going to have to update the data there. And that's also how we know when SQLite releases a file lock, when it goes from write mode to read mode.
I see. So this is SQLite's own VFS layer. And
yes.
Interesting. And so I thought it was actually just your Linux VFS. But so for SQLite VFS, do they give you all the information that you need to do basically like every single operation on the file is going through VFS? Which is more than just open and close and read and write, right? It's like, how do you even know the lock file status of SQLite, right? Because that typically is not a VFS thing, but it sounds like it's a SQLite thing.
So it is part of the SQLite VFS layer.
Interesting.
Every single syscall goes through a VFS layer except for memory allocation. That's it.
Got it. Okay, so I see. So if you can build, it's like, you know, your sounds like you know, this Verneuil, I guess, is built with C, right? It's because SQLite, I think it's also C as well. So you have to actually get it registered, a VFS layer into SQLite and intercept things. Interesting. And so, yeah, I guess tell us a bit more. So it sounds very simple. Just get in, things are done. But is it really that simple? Like, what was the hardest part building this in general?
So I think if you want to do something simple that just like copies a file whenever it's in a consistent state, that's pretty simple. And I think it's a nice exercise. And it's actually pretty much where we started. So what we thought was instead of trying to like compute diffs explicitly, we're going to come up with a simple snapshot format that can be deduplicated efficiently. So you have you go from snapshot A to snapshot B, and there's very little difference between the two. Then hopefully you don't have too much work. So he actually started with just compute full snapshots all the time. That was like V0, just to get something going and like test the code.
Yeah. And
then we said, okay, how do you get deduplication? So we divide the file in 64 kilobyte ranges. We call them chunks. Usually they map directly to SQLite pages if it's configured to use 64K pages. So that way, like the B tree writes are optimized for the same granularity as our replication logics. Like the things can just work out.
Interesting. Yeah, but then how did you? So the whole point is I just want to find the diffs, right?
Yeah.
Instead of trying to do the full snapshots. Yeah. And then so you hash every page?
And so we hash every single 64K page, and then we store a list of all the pages in what we call a manifest. So that's just, here's the content of that file. Got
it. And so that could be a pretty big file, right? If you have lots of data, right? So you do 64K, so do you do your own content hashing yourself, or does SQLite provides you already, or?
Yeah, no, we do. We have to do our content addressing ourselves. All the hashing we do ourselves. And so we looked into like using like a crypto hash, like SHA or whatever. But we already had a hash that's pretty good, and that's kind of made for deduplication in-house at Backtrace. It's called the UMash. So it comes with, it's comparable in performance to like murmur hash or something like the classic in-memory hash function, but it has 128-bit output, and it comes with collision guarantees. So.
Oh, interesting. So this is like an in-house implementation.
Yeah, it's open source as well on the GitHub repo.
Got it. What kind of guarantees does it provide? I'm very curious because hashing is a really hard problem to figure out in the first place. Like there's a bunch of trade-offs here, right? Like speed, performance, and but guarantees is I mean there's definitely like colliding and collision, like there's different kind of guarantees. What kind of guarantees do you need when it comes like duplication?
So all it offers is universality. So it's epsilon universal. So that means we know, given the input size, if you compare the hash for two different input size, we have a bound on the probability that the full 128-bit hash is the same.
Oh, I see. So because there's the probability of collision may be unbounded, I guess, depending on what kind of hash you use. So so this is that probability very, very low that you don't worry about it at all, or?
Yeah, that's it. So like, first off, like, well, what does it mean? Like once you have a function, either it collides or it doesn't, right? Yeah. So they're parameterized functions. You have to generate a pseudo-random or random key ideally. In practice, it's often like crypto-random.
Yeah.
And then you say over the set of all keys, what's the probability that two input collide? And we say, so what we have is, as long as you don't know the key, or like the key is generated independently of the input, the probability of collision for something on the size of like 64K is like 2 to the minus like 70.
Yeah. So the YOLO factor is much more lower here.
Yeah.
But I guess it's probably not the worst case if you, well, if you do have, you miss pages, I guess, right? You miss of replication if you somehow get into that little tiny percentage. Yeah.
Right. So yes, so that's in the very worst case. I'm not convinced that it's like, maybe if you craft your input very spatially, you can achieve that in practice, like the real probability on like non-adversarial input.
Yeah. Okay.
Should be better.
I
And so if you look at the probability, like if you do like a birthday collision bound, like it's very probable that if you do have a collision, the one that you're going to overwrite might just be dead data that you're not referring to.
I see. Got it. Okay, that's interesting. Okay, so you do your own hashing every single time there's a change, or does the VFS SQLite actually tells you, okay, I'm writing to this page, and I need to just do the content hashing at that time and just update my manifest file.
So yeah, when we do that right, we know exactly what range is written. So in the worst case, we have to like wait until the end, like, because if you write to half a page and like we're not gonna, maybe you're gonna write to the other half of the page later, who knows? So in the worst case, we always wait until you release the lock, and then we know all the page and all the chunks that have changed, and then we hash and upload them. However, we do know that most of the time, the sizes will just match and will be aligned. Most of the time, if you configure SQLite to be nice to us, then each write will be just very nicely aligned right to exactly one chunk, and that we can hash and like prepare for replication like on the fly.
Oh, okay. So do you have your own background worker doing this hashing constantly, basically, in your code as well, or?
Yeah. So yeah, no, the hashing is and like copying the data to be ready for upload. That's the only part that runs synchronously with your application. And so that's what we care about performance, because it's not in the background. If we use a slow crypto hash, then your application slows down.
Okay, got it. So I guess, going back to the original question, well, what is the biggest challenges to work on this? Like, it sounds like figuring out the things to actually able to hash, right? Figuring out how to duplicate the data, when to actually do the hashing, when to actually send off the copies. And so it sounds like those are the details that have to be figured out, right? Is it that the main things, or are there other things that are really hard to figure out in this?
I think these were the details, but it's kind of like, well, you look at your constraint and you kind of chip away at your design space, and you're left with not much. But I think the interesting problem was how do you, well, clearly we don't want to upload to S3 synchronously while you're trying to just commit your SQLite transaction. That's just super slow, right?
Yeah.
So how do you communicate between your application and like the synchronous part of determining what has changed? And you send that for an upload worker in the background that can send to S3.
Interesting.
So like you use a queue, obviously, right? You start with a queue, but then the problem is, what happens if the background worker is stuck? If your queue just grows unboundedly, then that's a new failure mode, and that's something we want to avoid.
I see. Got it. And so what is the choices you're making here? Are you saying like a bounded queue that starts dropping pages when we can't upload? Or I guess that's everybody's problem, right?
Yeah. So like that's not a good option, because another thing we want to make sure is that what data you do does make its way to S3 is valid. Like we don't want a broken snapshot, because then you try to recover from that and it's a nightmare. So what we do is we use a mix of, like, if you look at the problems, like it's very similar to like lock-free programming. So you have in the synchronous part where you figure out the diffs, you want to always be able to push your diff without blocking something goes wrong on the other end, right? So a bounded queue that blocks, no go. And then on the consumer side, you want the consumers to be able to make progress and like start uploading stuff regardless of what happens on the producer side. Even if they crash, we want to be able to figure out what stuff to upload. So that's very similar. So like on the producer side, you want something that's wait free. On the consumer side, you want something that's lock free.
I see. But that's an improvement in performance, right? It doesn't really, like, my network's down, we're stuck.
Yeah, this is not about performance. It's not about like having fresher snapshots. I think realistically, it probably slows things down a little bit. It's just about the worst case guarantees when something goes wrong.
I see. How does wait free and lock free give you a better guarantee then? I guess I'm not really clear. Like, because typically it just means you have a faster way to do things, right? How does that guarantee you in the worst case?
So typically, like wait free solutions are always slower than using a lock, pretty much always. The one thing they give you is you're going to make forward progress in like a bounded amount of time, regardless of what might be going on elsewhere in the system.
Got it.
So that's kind of what we're looking for. We're okay with taking a hit on performance as long as the worst case is that you never get stuck.
Interesting. Okay, I see. Okay, I roughly kind of understand what you mean. So what? I guess one thing I'm very curious about, right? Because there's the choices you have to make are kind of what we talked about, but also like when it comes to like storing the snapshot and storing the diffs and reloading the diffs, because that is not a natural SQLite thing, right? You're doing your own hashing, you're doing your own manifest file, and you're doing your sort of your own. So you have to reload your snapshot yourself, I guess. So you have to have your own reloading code that understands how to read things in your own way, right? Is that just an obvious choice? You just store things and just bytes and store things back to bytes, and like, or is there even more thoughts there to like figure out like what is the more efficient way to do this?
Yeah, pretty much. We went with the simplest possible approach. So like when it's just like, how do you buffer these things that you have to upload to S3? Each blob is one file. The file's name is the blob name. It's a horrible solution. Don't do this at home, but it works. And so the one thing special that we did is SQLite is also very careful about crash safety, like hardware crash safety. If your VM goes down or your machine goes down, it will come back up, and hopefully there won't be any data corruption. And it does that by just f-syncing data super frequently, right? That's why SQLite is so slow. We don't want to do that for our own buffer data because we have so many files. If we have to f-sync all these files, it's going to take forever. So instead, what we do is we use subdirectories that are tagged with a boot ID. So if something happens, the machine reboots, you're going to have a different directory name, and you won't have any state. And then we built a whole system so that you can restart from an empty state.
Empty state, but doesn't that mean I guess maybe I'm not understanding it correctly, that empty state basically means you have no snapshots? You basically have to forsake everything you've done before? And
yeah, so in the interest of robustness, we're like, well, you probably don't have like a hardware crash too often. So yes, it does mean that like you're going to start replicating and you think nothing is in S3 after a reboot. So you just upload like a lot of data.
Yeah.
But thanks to the content addressing, at least like you're only paying API, but not storage. Because it's going to go to the same blobs. Okay, well, it sucks a bit, but not too bad.
Okay. So you're also using the content hashing to know what files to write. And so if that exists there, you don't have to redo it. But but you're doing hashing on like pages though, right? So you're not writing a file per page, right? You kind of have to bundle it, right? S3 is not easy for small files. It's a pain. So do you do a hash on top of hashes to figure out like this is the number of pages I write, or just?
No. I mean, we should do something smart, but right now, just to keep things simple, we just do one blob per 64K page, and then we even compress it. So most blobs are like, I don't know, not even maybe 10, 20 kilobytes.
Yeah. Okay. So that makes things simpler. So you're treating it as a key value store almost, right? I'm just gonna write bunch of stuff as a key, and I can always read back. I already have that key. I should guarantee you to have the same page, and I have to kind of skip things, right? Yeah. I see. But then when you have a load up, you actually do a listing in that particular folder to make sure you have things. Just use S3.
We just do blind writes right now.
Got it. Okay, so even simpler. Got it. I see. Okay, because it doesn't matter, right? If you can overwrite it, the right files, you're good.
Yeah.
Got it. That's interesting. Cool.
Yeah.
And so I guess what is the choices, because you have Rust code and you have C code. The C code is for VFS, right?
Yeah.
To inject into VFS and understand some of the nuances of SQLite, or
Well, it's
yeah.
the C code is just the VFS layers, and the reason it's in C. The first is we started with a modernized like Linux VFS that was in C just for easier testing, and then we said, all right, let's make that our base VFS to intercept everything that's happening. And the other is like there's a lot of like low level, like essentially every single method in the VFS layer for SQLite maps to like one syscall. And the only thing that's important is making sure that you can just retry and list all the error modes and handle that correctly, like SQLite expects you to. So it's honestly easier to do that in C than to do that in Rust, where it's like, okay, Rust is going to make a C syscall, then it's going to return me an error. I have to figure out what this means at the syscall level and then return back to SQLite.
Got it. But the main logic of all this sort of hashing, all this queues, is in Rust, right?
Yep. The only thing the C code does is like, okay, a write happened, Rust figure out what to do. Or
got it. So you pass it to Rust. I see.
Yeah.
I see. And Rust has like I'm somewhat familiar with Rust, but I haven't done a lot of Rust yet. It has a very natural C interface for you to kind of interject with, or you don't have to do crazy FFI kind of things, right?
Correct. Yeah, you can't say like this, export this function as a C function.
Oh, yeah, okay.
It just does a thing.
Nice. Got it. Cool. And so, maybe as a, we're going to do a demo, just to kind of show out what it is. But one thing I always found will be fun to do if you have any things in your mind to show, hey, this part of the code is actually something really hard to figure out. Do you have an example you want to walk through? Maybe part of this, this is actually one of the things you took a long time to kind of figure out how it works.
Yeah. So I think the part that's really interesting, maybe is the replication buffer. So like you said, like you typically you'd use a queue, but you can't use a bounded queue. You can't use an unbounded queue. So how does this work? Especially given like the progress requirements that we have.
Yeah, feel free to share your screen, by the way. Yeah. If you want to walk through a little, let's try it out.
Let's see. All right, how do I share? Here. Let's share. Okay. All right, what do you see? Oh, is it good?
Yep, that looks good. Yeah, awesome. You have
all right.
Yeah, that's cool.
Yeah. So here's what happens when you say please store replication data in this directory. Then you're going to start like creating a super long subdirectory, which has, like I said, like we use a boot ID to make sure that you always get fresh data when you start from scratch. Then we derive some unique name from the SQLite DB file. And so what happens here is that whenever we close a transaction, when we release a write block, we're gonna start computing a diff, and we update the manifest in the staging subdirectory. So the staging subdirectory is always up to date, but if a write is happening, then like you're not gonna get a consistent snapshot, right? So if you have to be careful about how you use it. So in order to guarantee progress, like when maybe like you're writing like all the time to this file and you can never get a consistent read from staging, what we do is at the end of the write, once we've updated the manifest, everything is good to go in the staging directory, we check if there is a ready subdirectory. And if there is not, we create a new one. And that ready subdirectory is always consistent. It's write once.
Oh, got it. I see. So staging is just like in progress things. Once it's ready, you can just move it over there, right? Yeah, as a final place to store. Got it. Yeah.
Right. And then at some point, like the background workers will notice that there's some work to do in the subdirectory. They will say, oh, hey, there's a ready subdirectory. Let me rename that to consuming. And once it's renamed to consuming, I can upload all the blobs. Then I can upload the manifest and then delete everything. And at some point later, then another write will come in and notice that there's no ready subdirectory and create a new one that's a new, consistent, up-to-date snapshot. So that's how we guarantee progress when like there's always constant write churn. The problem here is that what if you have like a burst of writes? the first one gets to create a new ready subdirectory, and then you have like 10 more that come in later, but the ready subdirectory has already been created, so we can't touch it. And now you're going to be late forever because no one is ever going to write to the database again. That would suck. Like, we don't want that. Like, we're okay with slow replication, but infinite delay, no good.
Got it. Yeah, yeah.
So the fix there is to notice that, well, when no one is writing to the staging subdirectory, it is safe to read from. So we're going to do that kind of like a seclock kind of trick where we try to detect when a read happens. So we snapshot the manifest file, then we read all the chunks, and we upload them. Once we see that there's no more chunk left to upload, we check if the manifest file is still the same. And if so, then we've uploaded everything that was necessary for that manifest file, and we can update the snapshot on disk. Otherwise, that means a write is in progress, so we'll get a new ready subdirectory soonish. So that's how we get both like progress when there's a constant write stream, and also catch up when there's no more write.
Ah, got it, got it. So you kind of have to like have a mode, like a state machine here, like, okay, we're safe to actually do the staging reads because we want to make sure we can, try to start as soon as we can. But I guess when writes happen, it's almost like a read-write lock almost, right? Like when the write happened, we're in a different state now. I want to be more careful because things are changing. That's kind of what it seems like, right? Yeah, yeah.
Yeah, so we always try, like we always read from the ready, then we try to opportunistically see if we can get something from staging. And if not, then too bad.
Interesting, got it, got it. And where does all this code happening? If somebody's really interested in peeking your code repo, like where should they look?
It's this mega file that I should have broken down. It's replication buffer.rs.
Okay. And that has a state of deciding what to do in the replication.
So that's all the primitives, and then on the read side, that's all called from a copier.rs. Just like this just huge function that goes like all the steps and say, does this work? No, all right, let's try the next one. And on the right side, it's in let me make sure I had the right name on this one.
Got it, got it. Cool.
Yeah. Yeah, on the right side is tracker.rs because it just tracks changes.
I see. Okay, got it, got it. Cool.
Right.
Sounds good. So let's do a demo then. Let's see how this works in practice. Because I'm not having to write CCs and stuff. Okay, got it. Do you have yours? Maybe we should run on yours because you probably most likely have it ready, right?
Yeah, for sure.
Okay, yeah.
All right.
Just to make it simple. I'll just cut my tryout on editing. So.
All right. I'm going to use two windows. Okay, I'm going to share my whole screen because we need yeah.
Sounds good.
Okay. Oh. So I built the VFS with just cargo, and then we have a config file. So what it says here is like, where do you store the data that you want to upload to S3 and then where to send it.
Got it.
And then look at my host name. That's okay. Let's see, make sure we start from scratch. So you don't need to you can just start from any hot, any SQLite database with some data. When you start replicating, worst case, we'll just send a full snapshot from scratch, but I think it's nice for the demo to know where we're starting from. All right, so we're in the SQLite shell. We configured some environment variables that will be picked up by the extension once we load it. So step first, we load the extension.
Cool.
And then the second step is we're going to open this file on disk, just local file, and we're going to say use the Verneuil VFS instead of the regular Unix VFS.
Okay, cool.
Okay, so we can go like yeah. So chat.db has been created. There's nothing in there yet. Let's
Nice.
start by
Schema.
create. So we can create our table here.
Yep.
And that was in a transaction, right? Everything is implicit in a transaction at the SQLite shell. So when the transaction closed, it kicked off replication with Verneuil.
Ah, okay. Yes. So that's already happened.
So we can, yeah. So we can go in the console here. So like, you know, it might be like a couple of milliseconds before it gets started, and then a couple hundred milliseconds to get all the files, but eventually it gets there. All right. So this is our manifest file. You can see it has the host name and then the path of the local file on disk and some hash prefix to avoid hotspots. And there's only one page in the file. Cool. The file is super small.
And right? do you do, because this is less than, of course, a page, right? But you do it because there's nothing else going on, right? Like, exactly. Right? Because you have a lot of writes. I remember you talked about like we wait until the full walk is finished and that kind of thing. Yeah. Cool.
And the other thing that's nice about like the replication buffer design is that because it's very robust to whatever happens on the write side, on the read side when we consume and upload to S3, then we can just slow down however we want and know that we won't have too much of an impact. So that's what we do to make sure when there's too many writes, we just say, okay, well, there's a rate limiter on like writes to S3 and we just sleep for a bit.
Got it. Cool.
Okay, and then we're going to do the same thing here. So I have this read config. I will paste it later. Actually, let's paste it now. And it's essentially the same thing. Like we have to know what buckets to read from. And then it's nice to have a local cache directory so that you don't keep re-downloading the same blobs.
Okay, nice.
So we load the extension and then we say open this file, but this file is going to use the Verneuil snapshot VFS. And we have this Verneuil URI that says it's not actually a file. It's an URI. So you have the host name here, and then you have the path of the local file on that host name. And from that, we can compute like the name of the blobs in S3. Right.
Very cool.
So we got something here. Let's see what's in the data. Oh yeah.
There you go.
The schema we created. Woohoo! All right, now let's write something to that table. Let's say, hi, Tim.
Nice.
Okay. Again, this was one transaction, so it's already replicating right now. Then what we can do here is, so if we try to read, say select star from history, it's going to be empty because we still have the old snapshot. We have to ask for a hard refresh.
Okay.
So we got a refresh. Then let's see what happened here. Whoa!
Wow.
And that's so I think that's like what I find very nice about this approach is that you can just slot it in an existing application, even like the SQLite shell, and we'll start doing things.
Wow, that's cool. Yeah, and so you're doing all kind of behind the scenes. And I guess what's interesting is, I mean, this two standby, this is not the purpose of this, right? You're really just trying to make sure that you can always load back in. So there's probably no need to do a hot refresh of your snapshot anytime. Is there any need to actually have a hot refresh of a snapshot? You know, even in production for you guys, or?
Yeah. So currently, no, because a lot of the things we do is like offline analytics and like low priority work, but we are going to build much more on top of the read replicas, and then like having data that's a couple seconds old is much nicer than having data that's a couple hours old.
Wow, interesting. Got it. And that's really cool. And so like, yeah, it's like basically like this change data capture almost kind of thing, but I guess it's not meant for that, right? The demo looks like that, right? It's like, oh, you can do a different, like, is that what's going to be the future of this? Is this just a replication backup tool? are you planning to do even more crazier stuff in the future with this, or?
So like the future, I think 100% is going to be read replicas that are, a couple seconds to maybe a couple minutes stale. Like one of the things looked into was, do we want to turn this into a change data capture tool? And then because of our requirements on failure modes, where we can't just buffer an arbitrary like history of this is all the changes that happened, and that's not in our scope. So it's really just read replicas that are updated from time to time, hopefully frequently enough for you to have like fresh data.
Got it. And I guess we haven't touched on this, but what is the purpose of open sourcing this? Are you guys, because it's just not a product, I can just open source it and everybody can use it, or do you hope to get contributions from the community as well, or?
I mean, I think contributions are always nice, but it's mostly because, yes, like you said, it's not like a product. It's not something we're not going to sell that for sure. And I think it's useful. So it's like, hopefully, like we do good to others, then people will do good, and like everyone benefits.
Yeah. Did you have any other interactions when it comes to other open source projects you guys did? I guess, yeah, I'm just curious, is there any fun interactions based on open sourcing? Do you see other people pulling and using in production, or what are side benefits of being open sourcing your tools like this? Because not everybody is doing this yet, right?
Yeah, I think for us, like maybe because our tools tend to be kind of very situated and target interesting, maybe weird niches. Mostly what we get is because it's open source, we can get a review from domain experts. So like with UMash, we always were going to open source the hash function, and we managed to get like design and code review like very quickly from like Colin Percival, or from a researcher who specializes in hash functions. And like that's not something you can easily do if it's going to be closed source, because then it's like, oh, okay, do I have to sign an NDA? You want a paid contract, that sort of thing. If it's open source, I think it's easier to get access to really deep expertise.
Oh, wow. And so interesting. I never thought about that actually. So you have easier path to ask someone, hey, can you please review this project? And are they all pretty open to review, or do you have like, is it pre-existing relationships? I haven't seen that in practice a lot.
I think it's a lot of people having pre-existing relationship, and but so obviously like you need something else. You need something to open the door, like a cold call. I don't know if it's going to work, but the fact that it's open source makes it a lot easier. Got
it. Wow. And I'm sure like there's plenty of people actually run into this problem of actually need to replicate your SQLite projects, right? Did you see people actually already using this in the wild, or?
I don't know. I mean, I think if you're trying to get started, the light stream project is like it's much more polished. It's easier to get started for sure. So I assume that's where people are going.
Got it. And so
if they don't get, but they don't try to get read replicas, so that's the hard part.
Interesting. So if people do want to try this, what's the best way to get started? Just go to GitHub, go to the repo, follow the README. Is that good enough, or?
Yeah, I think so. So if you clone the repo on Linux only, and there's an example that starts a RustUI integration. So it's just a self-contained program that uses regular like Rust libraries to interact with SQLite. And just loads Verneuil at runtime, and it starts replicating for you, and then it reads from its own read replica. Got
it. Very cool. Nice. Well, hey, this is super fun. I think this is actually a super useful, library, and this actually has a lot of details. Actually, definitely we didn't go into like that much detail, but it's actually really cool to see the choice of making the performance trade-offs, right? And the hashing, the finding out the duplication and stuff. Yeah. So if people want to reach out to you, what would be the best way? Do you have Twitter or
yeah. I'm at Khuong on Twitter, but if it's like specific to Verneuil, probably just open an issue and or a question, and someone will look at it. Hopefully, like I look at GitHub at least once a week.